Hi, it's Mike Power, and here's a look at our East Goldfield project. And first, a quick word from our lawyers. This story begins in the late 1890s in Nevada. Things were grim. The mines had shut down, the cattle business was in decline, and people were leaving the state. Southern Nevada was virtually uninhabited and unexplored. Aside from a few nomadic native bands and itinerant prospectors, there were just a few ranchers working small homesteads up in the mountains where there was water. This all changed in May 1900 when rancher and part-time prospector Jim Butler discovered high-grade silver at Tonopah. The fantastically rich discovery saved Nevada, and Tonopah quickly grew into a boomtown, becoming the jumping-off point for exploration to the south, east, and west. Now, Jim was a generous man with an eye for the main chance, and so was Tom Kendall, who ran one of the first saloons in Tonopah. Thus, when a roaming prospector named Tom Fisherman showed up in late 1902 with an unusual specimen of very high-grade gold ore, they were interested. They advanced Tom the large sum of $10 in return for him showing them the find, and Tom promptly disappeared on a bender. Undismayed, they hired two local boys, Henry Stimler and Billy Marsh, to track down Tom, sober him up, and convince him to show them the find. Tom led them 30 miles south of Tonopah to the next range of hills in December 1902. There, on the side of Columbia Mountain, huddled behind some rocks to escape a sandstorm, they noticed flakes of gold mixed with dirt in a puddle. They staked the sandstorm claims and returned to Tonopah. The rush was on. Prospectors quickly converged on the site of the strike, and Goldfield was founded in the fall of 1903. It grew to become, very briefly, the largest city in Nevada with a population of over 20,000. It was a wild boom town. The camp was quickly staked by small-time prospectors and miners who initially developed it using the leasing system. This is where two or three miners would extract the ore and ship it directly to faraway mills, splitting the proceeds with the claim owners. They could do this because the ore was fabulously rich, with visible gold common in the richest lodes. At the Mohawk mine, one 47-ton boxcar of ore returned 28,700 ounces of gold at an average grade of 609 ounces per ton. That's $118 million in our depreciated currency. In later years, Goldfield Consolidated Mines scooped up the claims once the high grade was gone. Goldfield produced continuously into the 1950s and has produced gold sporadically since. By the late 1990s, it had produced 4.2 million ounces at 18.78 grams per ton gold. But the heady boom time days were over. Since about 2000, exploration in the Goldfield District has languished. Amid low gold prices and a lack of interest in exploration along the Walker Lane until recently. During that period, Waterton quietly consolidated the district. They picked up claims and they bought Junior, took it private to consolidate the district. 5 years ago, Centerra Gold Corp moved in. They bought the project from Waterton, conducted district-scale exploration, and last August announced they were going ahead with production, starting with their smaller oxide resource. And as of this spring, there's a mine being built in Goldfield. Initial resources are about 800,000 ounces, and that's just primarily the oxide ore. There's a bit of transition ore, and it's from four deposits, the Gemfield deposits, the main show, but they hope to take resources from the Goldfield Main, Jupiter, and McMahon Ridge deposits. So things are looking up in the Goldfield District again. And that's good news because Goldfield is a world-class gold system, and there's likely lots of gold left to be found. Goldfield is where high sulfidation mineralization was first identified, and it's nicely outlined by quartz alunite alteration. You can see it from space. This is aster imagery processed to enhance alunite, potassium aluminum sulfate, which is closely associated with gold in the district. Overall, the alunite anomaly looks like a frying pan. Here's the pan and here's the handle. And here are the four deposits that Centerra is planning to mine, clustered around the rim of the pan. The district is staked solid with Centerra, Kinross, and Barrick holding the pan, and little old Silver Range holding the handle. And there's gold out in that handle. And people have been looking for it since about 1907. There are well over 100 workings on the property. Here are some of them that we have mapped, the most advanced of which is the Tom Keene mine in the center of the property. The Tom Keene mine was developed down to about 500 feet on 4 levels. It was discovered in 1907 and developed by an incline shaft. There have been several rounds of production at the mine between the period of 1910 to 1930. Unfortunately, no documented records. In order to understand what's going on at Goldfield, we need to take a short geologic digression. High sulfidation deposits, first recognized at Goldfield, form in calco-calcic arcs, generally within the volcanic pile, and above subvolcanic intrusions that are enriched in copper and gold. In fact, many high sulfidation deposits are directly above economic copper porphyries. They're composed of two components. The first is the feeders. These are steeply dipping, high-angle structures. They're not very wide. Miners used to refer to them as ledges. They generally host very high grades. These are the very high-grade deposits at Goldfield were hosted in the feeders. They extend to surface, but where they do, their expression can be quite cryptic because they're often plugged with breccias. The stratiform mineralization, on the other hand, is quite extensive, and it consists of lower grade mineralization and is peripheral to the feeders from whence it derives its mineral endowment. So the bulk of the gold in a high sulfidation deposit is actually in this lower grade rock. But you need those high angle feeder structures to give you the little boost in grade that makes these deposits truly economic. High sulfidation deposits are found within alteration zones in a volcanic pile called a lithocap. The same alteration processes that create the lithocap are responsible for the high sulfidation deposits. Lithocaps form when acid fluids, that is superheated water, carrying fluorine, chlorine, and hydrogen sulfide, mix with near-surface water to create very strong acids. These progress away from the conduit into the host rock, progressively eating away at the rock. Where the fluid is extremely acidic, very low pH, all that's left is some residual quartz. But as it moves further into the volcanic pile, the pH rises and the alteration minerals that are left behind change. Close to the conduit are zones of residual quartz. Generally, this residual quartz is vuggy because the host rocks often contain phenocrysts of plagioclase feldspars that are easily eaten away, and these leave the holes behind, and the finer grain material is just residual silica. If, however, you're dealing with a protolith that is dominantly fine-grained, you can end up with a rock that's just entirely silica. The same processes are at work. The alteration zones show a progression in mineralization from quartz through alunite into kaolinite and finally into smectite. These alteration zones can be very extensive, and the high sulfidation deposits are confined within the lithocap and can extend a great distance away from the source intrusion. Here's an example from Iran where there's a large lithocap here on the right of residual quartz, and it's grading into the peripheral zone of advanced argillic alteration. That's more the maltmerilonite smectite. So the source of the alteration would be over here, and it's been progressing this way. Heading back to East Goldfield, we'll see a lot of these features. The geology in the East Goldfield project consists essentially of two major pyroclastic units. There's a younger pyroclastic unit down here, it's relatively undeformed, and an older one out here, and they're juxtaposed against each other along a structural zone you see right here. When we superimpose the alunite alteration on this, you can see that the alunite alteration, where the lithocap is forming, is most intense right here, just north of this structural zone in the older tuff units. There are numerous ledges that have been mapped on the project. These are shown here in blue. These are the remnants of the feeder zones. By no means all of the feeder zones, however, because there's also a lot of breccias on the property as well. And these could be hiding the cryptic feeder zones that we can't yet see. There's lithocap on the rock. It's down in the southwest corner of the property, and it consists of fine-grained silica, like you see here and here. Some of it's a little bit vuggy, but most of it is fine silica. You see little ghosts, little white ghosts of pumice clasts that were altered within it, but the rock is entirely silica. Most of it's flat lying, but it's been lifted up along a fault here. And there are extensive hydrothermal breccias on the property. They generally look like this. The key feature of these hydrothermal breccias is that the cement is iron oxide. In this case, it's sort of a dark limonite. Over here, it's more goethite, limonite kind of color. The breccia contains clasts of basically all the rocks in the area, including some of the overlying dacite to the north. The breccias are relatively extensive compared to the ledges because they've come up along some of the faults. This is a long section, so we're looking along the quartz alunite ridge here, and along some of the inferred low angle faults, you'll find breccias coming to surface. And because of the attitude of the breccias, they rake off to the east relative to the generally sloping topography. You end up with some large exposures in places of breccia. This is a gold project, so let's look at numbers. We'll start with dirt and move down. Here's the gold and soil anomaly. There's anomalous response along the length of the quartz alunite anomaly here. This is on that high ridge. But there's also response in the flat area to the south. Here's gold in surface samples collected to date. The results are pretty spotty, reflecting the difficulty in surface sampling these highly altered rocks. But as you go deeper, it's a different and more promising story. Here's a summary of the top 10 hits by grade and grade thickness from 45 historic drill holes on the property. There are some pretty good numbers here and some decent width, but it's pretty clear that the gold is at depth. We're not finding lots of it at surface. In the area of the Tom Keene mine, where the drill density is highest, we've got a target coming together, which provides some insight into what a gold deposit might look like on this property. In this area, 18 drill holes nicely define a gently southeast dipping gold-bearing horizon. The drill data define a stratabound gold-bearing horizon between 7 to 18 meters thick, about 100 meters below surface, which could contain 50 to 70,000 ounces. Now, I should caution, this is not a resource. This is just a target for exploration, and it's based on historic data. We don't know the full extent of this target. It's open in 3 directions, and it's just confined to the area of the Tom Keene mine. But it poses some interesting questions. How much further might it extend? And could there be a series of these stacked at different levels in the gently southerly dipping stratigraphy? Got to be drilled. The bigger prize, however, is what's up here in this quartz alunite anomaly. The handle of the frying pan that hosts all the deposits in the Goldfield District. Well, we think we have a model that explains what's going on, and we're getting ready to test it. Our mapping to date, and we'll look at a cross-section along here, indicates that what's going on is that we have basically a bit of a push-up structure, if they call it a flower structure. We have a number of faults coming up here. Bedding progressively steepens as you go across it. These faults in many places are plugged with breccias. There's intense quartz alunite alteration. That's this shadow here. It's cut by some ledges. And in the area of the Tom Keene mine, we've actually defined a target for exploration supported by a number of drill holes. So we're starting to see the picture here. The target at Tom Keene is very small compared to what might be underneath the core of the quartz alunite ridge. And that's where we want to go next. The big prize lies here. How big could this be? Here's an analog, the Lepanto deposit in the Philippines. This is a flat-lying, nearly blind high sulfidation deposit. It outcrops in only one small area, right here, along a steep cliff face. The rest of it is completely blind. buried under 100 to 200 meters of barren volcanics. There's an extensive quartz alunite alteration halo that surrounds the deposit, but it outcrops only along the edge of the overlying volcanics. The Lepanto deposit hosted nearly 4 million ounces of gold mined between 1946 and the 1990s. If we head back to Goldfield and zoom out a bit, we see that the Lepanto deposit and its alteration halo would fit nicely inside the handle of the much larger frying pan, the quartz alunite anomaly that hosts all of the gold deposits in the Goldfield camp. So what's next? Well, we're planning a 60-kilometer 3D IP survey to cover the whole property. We think this survey will be able to accurately image the resistive, that is the residual quartz zones in and along the quartz alunite ridge and in the area to the south. We think that using that data, we'll be able to define some really good drill targets. That survey is going to cover over 5 kilometers of strike in some of the most prospective ground in the Goldfield camp. We're pretty sure we're going to end up with a pretty good looking target when this is done, and then we're looking forward to drill testing it. So stay tuned.